There's a herd of sheep. And then there's the sheepdog and there's the farmer. And this one sheep says, I tell you, the man and the dog are working together. And the other sheep says, oh, you and your conspiracy.
Lee, are we ready to go? Okay, are we waiting for Lucy or not?
No, it's okay. She's alright.
She's sheepdogging.
She's sheepdogging? Oh, okay. Alright, when Lee comes back, we'll start then. The long silence. Lee, where are you? He's back. Shall we start, shall we, Lee? Okay. Alright, I'm honoured to introduce Michael McCulloch from the University of Plymouth. And the reason I want to introduce him is because he's, like us, he's part of the crisis of physics, an expression of the crisis of physics, or indeed the crisis of science now. And he, like us, and well, me in the weather, people who have been involved in the electric universe for longer, and Mike McCulloch have all suffered from establishment wanting to ignore us and avoiding questioning things. So that is the reason why I want to introduce him, and he's got very important things to say. And his ideas about galaxies and other things do overlap with some of the new ideas in electric universe, and also deal with problems I encountered when I was doing galaxy formation and run into a lot of problems. I don't think any of us have answered everything at all, but I think overlap between Mike and what is been said in electric universe could be very fruitful. So, Mike McCulloch.
Thank you very much for inviting me. Okay, so the title is Quantized Inertia Gets Rid of Dark Matter and Predicts an Electric Rocket.
Louder, put the mic up to your mouth a bit.
Okay.
Yeah, just fiddle with this. Keep talking.
So I'll first talk about the stimulating problem, galaxy rotation, arguably the biggest problem in physics. Show that dark matter isn't good enough, introduce quantized inertia to you. I'll mention a better derivation of it as well, which is new work. I'll talk about the M drive, the Woodward effect, and other tests that can be made, and then talk about applications. Okay, so this is the Andromeda Galaxy, and most of the matter in the universe is in this form. Stars spinning around a galaxy like this, and I've indicated a star, the yellow star there, spinning around, so the speed of it, shown by the red arrow, and the centrifugal inertial force pushes it out, so that's a white arrow, centrifugal force. Gravity pulls it in, of course, and because we see galaxies as nice, round, stable structures, we expect the inertial force and the gravitational one to balance, but they don't. It appears that the gravitational force from the visible matter that we see is too small to hold the galaxy in, so they should fly apart. So what mainstream physics does, of course, as you know, is to add dark matter wherever it's needed arbitrarily to the galaxy. So they put the dark matter in where it's needed to make it all work out. And they lengthen this gravitational arrow. They increase the gravitational force of attraction that way. But there are many observations that falsify dark matter. For example, there's this one called Renzo's rule. If you look at the distribution of light within the galaxy as you go out from the centre, you get a graph something like this yellow one, and wherever the galaxy is light you get a peak, and where it's dark you get a trough. And if you look at the velocity curve, it always follows the light curve. So the two lines are go up together and go down together, and this implies that the dynamics is determined solely by the light matter, not anything else. So there are other reasons to doubt dark matter as well. It's not been seen after 40 years of looking, and also it's philosophically very unsatisfactory. What normally happens in physics is shown by the blue boxes up here. You propose a simple hypothesis, you test it on the data, and if it doesn't work you get rid of it and come up with a new simple hypothesis. So this process here. But with dark matter, it's very different. What they have is a system which is complicated enough to be compared with the data, and if it doesn't agree, they can adjust it. So dark matter is a very dangerous thing, actually, and I think it's installed physics because they can go on tuning it forever. So it's very like Ptolemy's epicycles in AD 100 that were complicated enough to be right for the wrong reason. Okay, so I'm going to discuss my alternative view. So I'm going to start with an oceanographic analogy. So imagine you have a ship parked next to a dock. Well, there'll be waves coming at it from the open sea and hitting it, pushing it towards the dock. But there'll be very few waves between the ship and the dock. And that's not just because the waves have been sheltered by the ship, it's also because only certain wavelengths of wave can exist between the ship and the dock. Waves that have antinodes at the wall or the ship will be damped by friction. Only those waves that have a node, a part of the wave that's not moving, at the dock and the ship will be able to survive and exist within this gap. So this means that there'll be more waves on this side of the ship than the other one, and the ship will move towards the dock. And if you can't see the waves, it would appear to be like magic that it's moving, but it's not, it's because of waves. So that's an analogy to what I'm going to be talking about. But there is another sea, the quantum sea, and we know this exists. So Heisenberg had his famous principle up here, states that the uncertainty momentum of an object, the quantum object, times its uncertainty in position, so that's momentum, uncertainty in position. There's got to be more than a constant, this h bar over 2. So whenever you shrink a volume down so it becomes very small, then the uncertainty in position reduces and the uncertainty momentum increases, and you get this quantum sea of particles, which are particles, as shown here by the blue arrows, so this one and this one. The particles appear as pairs to conserve momentum, and also as waves. Quantum mechanics says that we can't decide whether they're particles or waves. So this is a quantum sea. So does it exist? Well, the proof is a Casimir effect. Hendrik Casimir in 1948 said, okay, if this exists and you put two conducting plates very close together, then just like between the ship and the dock, fewer waves will be able to exist between the plates than outside them. So, for example, those two will not fit within the gap, and so now there'll be more waves banging into the plates from outside than will be pushing them out from inside. So the plates will have a force to push them, and that force will push them together like that. So this is the Casimir effect, and it's been seen. This is a paper from 1996 that detected the Casimir effect. So this quantum sea is really there. Okay, so, but that's using a kind of conductive plate. But there is another kind of boundary that I'd like to talk about, that I'm going to be using, and that's a horizon. So imagine that you're so shocked by what I'm saying in this talk that you run away very fast, like this person. Well, if you do it fast enough, you'll be travelling faster than the speed of sound, and then you won't be able to hear me anymore. The information that I'm saying will not catch up with you. So you could say that I would now be behind a horizon for you, an acoustic horizon. Any information I have, you would never be able to have it. So that's the idea of a horizon. And horizons exist in light physics as well, optical physics. For example, if you have a black hole or a very strong gravitational force, then you get a horizon from it, this circle here. And what Hawking did, about 1974, is say that what happens if a particle pair appears right in the boundary of this horizon, one particle comes out, the other goes in, and the idea of a black hole is that once something goes in, it can never come out again. So when that happens, the particle that goes in disappears from the point of view of anything outside the black hole, and the one outside is now free. It's lost its twin, so it's free. It won't recombine with its twin, it will come off as Hawking radiation. So this was the idea of Hawking radiation, which has not been seen yet. But about the same time, Bill Unruh in Canada, he came up with Unruh radiation. So here, The idea is that you have an accelerating spaceship and a horizon appears behind it, because this spaceship, it's like you running away from the lecture, cannot know anything about what's behind this horizon. This is called the Rindler horizon. And similarly, particle pairs come off. One is lost from the point of view of the spaceship behind the horizon. The other one becomes free and comes off as Unruh radiation. And this has arguably been seen, this Unruh radiation. The problem with it is that the wavelength of it is very long. So the formula is here, the wavelength is 8c squared over the acceleration, and c squared is a very big number, about 10 to the 17. So for any terrestrial acceleration of about 10 meters per second, this wavelength is a few light years. So it's very hard to see them. But they have found, there was an experiment by Bevis-Lewis. What they did was they got a gold nanotip, a very sharp pin, and they fired a laser at it, and excited plasmons that went round the end of the tip very fast. This constituted a very high acceleration, and they saw a strange radiation coming off. And it was proposed by Smolyanov, 2005, that this looked exactly like what you would expect from Unruh radiation. So it could be that Unruh radiation has been seen, but this experiment has not been repeated, but it should be repeated. Okay. So I'm going to use this Unruh radiation to explain inertial mass. So the idea is very similar to the ship and the dock. You have an object here which is accelerating to the right, and it sees a horizon to its left. And Unruh radiation will come off this horizon. On this side of the object, any wavelength can exist, because at the moment we're not considering any boundary at all, so you can have any waves you want. But between the object and the horizon, very few wavelengths can exist. And I've shown none at all here, but I don't mean that. There will be a few, but less. The idea is there are less. So there will be a force, more waves on this side, fewer on the other side, so a force pushing the object back against whatever acceleration it had. So I've managed to show, in this paper here, that this predicts inertial mass. So it explains why it's hard to accelerate things, why they keep going in a straight line. Okay, but what about the Hubble horizon? That's another kind of horizon. We're in the centre here. This is supposed to be the universe, and the further you go away from us, the faster stars are moving away from us. That's the idea. So that at a certain distance, which is about 10 to the 26 meters, they're moving away at the speed of light. And then we can't see them anymore. It's not possible to see them. The light can't get back to us at all. So there's a horizon there. So what does this do to the same picture? Well, if you look at the same picture, this means that even on the right-hand side of the object, some of the waves are damped. So you go from having a large amplitude to a slightly smaller one. So the Hubble horizon tends to mess up this process a little bit. And it will mess it up an awful lot if the Unruh waves are very long, because then very few of them will fit between the object and the horizon. So the prediction here is that for a high acceleration, you get an acceleration of the object this way, it sees Unruh waves, sees a horizon which damps them on this side, which pulls it back, the waves push it back against its motion. But for a very low acceleration, the arrow here is smaller, the wave is so long that they're all deleted or damped by the Hubble horizon. So this process doesn't work anymore. So the prediction of this model is that for very low accelerations, inertia will not work as we expect. And that's exactly what is needed to explain galaxy rotation. Because galaxies behave very nicely in the centre, where the stars are spinning around very fast. But as soon as the Unruh waves, and you can calculate this, become comparable to the Hubble scale, they start to misbehave. And when I apply my theory, then the centrifugal force reduces, the inertial mass reduces just enough, it's exactly right, to balance the gravitational force. So I'll show you some data in a minute on that. So just to become more quantitative, I published the original model in this paper in MNRAS, Monthly Notices of the Royal Astronomical Society in 2007. And I'm assuming two things. Inertia is caused by onward radiation, as I said, and only waves that fit exactly into the Hubble scale are allowed. So if they don't fit exactly, they get damned. And when you assume those two things, you can derive this formula here. So the modified inertial mass is equal to the original one times this factor where that's c squared, speed of light squared, that's the acceleration of the object, and that's the Hubble diameter. That symbol there is a very large number. So it means this is very small. This effect is incredibly tiny usually, but when the acceleration is very low, this term can blow up and reduce inertial mass. So it strictly violates the equivalence principle of general relativity. We normally assume that the inertial mass is equal to the gravitational one. So if you plot the acceleration along here and the ratio of the inertial mass to the gravitational mass here, you would get a straight line. This is what's expected. What I'm predicting is a drop-off of the inertial mass for very low accelerations. So the first result is that if you take this formula and you put it into Newton's second law and the gravity law, what comes out is the usual term plus an extra constant term, 2c squared over theta. And this is the acceleration that they see as the cosmic acceleration. It's the acceleration of the edge of the universe away from the centre. So this was what they found from the supernovae in 1999. It's the same number. So this shows the prediction of the model is that the velocity at the edge of a galaxy will be given by this formula here. So that's obviously the gravitational constant, the mass of the galaxy, the speed of light, and that's the Hubble diameter. So if you apply that very simple formula, and note that there is no tuning possible here, so I can't fudge it at all. It's only got one prediction, so it's either right or wrong, and it turns out to be right. Because if you look at different galaxies and you plot the system mass along this axis, and then the rotational speed of this axis, a log value, then the observations are shown by the solid curve. So for dwarfs, or spiral galaxies, and even galaxy clusters, quantized inertia predicts a dashed line, and MOND is very similar as well. But MOND, that's another theory that you may not know about, but it requires an adjustable parameter to work, whereas what I'm suggesting does not. Okay, so it fits the data that way. And this is data that I got from Professor Stacy McGough in the US. It shows the expected and observed acceleration of different galaxies, 153 of them. So this is the expected acceleration, this is the observed one up the y-axis. And if the theory was correct, if Newton was correct, you would get everything lining up along the diagonal. But this shows that for low accelerations, the observed acceleration is too high, so it's risen up above the dotted line. And the data is the squares. And quantized inertia predicts the dashed line, so it agrees with all this data. But it also predicts something else. It predicts that there is a minimum acceleration in nature, which is given by this very small number. This is very big, size of the universe, it's very small acceleration. But if the universe has been expanding, then the Hubble scale in the past was much lower. So in the past, the minimum acceleration must have been higher. So you would expect early galaxies to be spinning faster for the same apparent mass. And that seems to be the case. I actually sent a paper on predicting this to Nature in early 2017, and they rejected it, but then 3 months later they published this paper by Genzel et al., which is now very famous actually, which shows just this going on. You can see these are the accelerations of different galaxies. These are the redshifts, and you can see that for higher redshifts the acceleration is greater. If quantized inertia was exactly right, all these points would line up along this line. So you can see that the 4 closer ones are not too bad. That's not too bad. This is way off. But you have to remember that these are the first 6 galaxies that they've ever studied in this way. And, for example, this one existed when the universe was only 1/3 its present size. So they're looking at the very edge of their capability. There'll be more data soon, I hope. Okay, so I'll just mention a few things, other things that I can show. So these are a few anomalies I've been looking at, arranged in terms of scale and acceleration, from high acceleration, small scale, to large scale and low acceleration. So the cosmic acceleration I've talked about, galaxy rotation, the flyby anomalies, time-hour effect. I'll talk about the M drive in a minute. I also have some ideas about cold fusion, but I'm not sure about those yet, and the proton radius anomaly. But generally, it can predict everything that the standard theory can, as well as galaxy rotation and cosmic acceleration and these other things. It can explain inertial mass for the first time. We've never had an understanding of why it should be the case that things have a constant speed. It gets rid of dark matter, it's not needed anymore, no dark energy. And it combines quantum mechanics and relativity, because the quantum C obviously comes from quantum mechanics, and it's made inhomogeneous in space by horizons that come from relativity. Okay. I can also get gravity from this as well. I don't have time to go into this now, but this is a derivation in one of my papers. You can start with Heisenberg's uncertainty relation, momentum position uncertainty relation, and in a few lines you get Newton's gravitational law. It's quite simply done. So I guess I may not have time to go through this derivation, but this is a better derivation I've just been working on of the formula. You can start from Heisenberg's uncertainty relation. You assume that you're looking at photons, so energy is times c. So you can write this down. So the uncertainty in energy is equal to h bar c over 2 times the uncertainty in position. So I'm going to assume, and this is crucial in quantized inertia, that this dx in Heisenberg's uncertainty relation is determined by this Rindler horizon from relativity. So I'm going to stick the two theories together kind of drastically there. And I'm also going to assume that this uncertainty in energy becomes real. So if you do that, then you have an object accelerating. On this side it has no boundary, so the uncertainty in position is very large. On this side it has a Rindler horizon, so the uncertainty in position is very small. So you can write an expression like this. So you've got a difference in energy on the right and on the left. But a colleague of mine in Spain, Jaume Gine, pointed out that I could get quantized inertia exactly this way, and this is a new way of doing it. If instead of looking at the distance between the object and the horizon, I just look at the width of the horizon. Because in a sense we're looking at the uncertainty in position of a quantum particle which has been emitted from this horizon. So it's probably going to be the width of the horizon more than the distance. And if you do that, then for the uncertainty on the right you put in this distance, which is c squared over a. Uncertainty on the left, you just put in the Hubble scale, and then you use the undo temperature in the formula for A. You get T, you replace T with, you assume it's thermalized energy, and you get this formula. You can probably see where I'm going with this. If you know equals mc squared, it turns out you get this formula exactly, quite simply, by mixing quantum mechanics and relativity this way. And these are two theories that are not supposed to be able to talk to each other. But if you let them talk to each other, they explain galaxy rotation and these other things. Okay, so we've just submitted this paper to you. So as a pictorial summary of this, just to explain it, if this is an object accelerating to the left, it's a red arrow, then you can imagine that its uncertainty in position is very large this way, because there's a cosmic boundary over here. But here's the Rindler horizon on its right, close to it. If you look at Heisenberg's uncertainty principle, whenever dx is big, dp, uncertainty momentum is small. They're opposing, so the uncertainty momentum will be a mirror image of dx, like this. So this means that whenever there's an acceleration this way, the uncertainty momentum launches out in the opposite direction. That means it's statistically more likely that the object is going to move the other way. So it kind of explains it in a very simple way. Okay. So if this is all true, how can we use this? How can we utilize it in technology? If we have an object here which is spinning very rapidly, so it sees Unruh waves here, can we put an artificial horizon in, damp the wave so that the object moves towards the horizon, because there's a lot of waves pushing it one way, not the other. So maybe we can, because the Casimir effect does something like this. Again, the Casimir effect, waves outside, no waves inside, so it moves together. What if you had a V shape? You had a V shape, inside this gap there'd be fewer waves, there'd be more outside, so presumably it would then be pushed to the right. If you could somehow make the vacuum more energetic within the V shape, then it would push out and move the other way. Well, something may have happened like that. You may have heard of the M drive. Roger Scheuer, the British engineer, in 2001 he found that if you put microwaves into a cone-shaped cavity, it moved towards its narrow end. So it could be an experimental error, still nobody's found an error yet. And NASA and other people have looked and found the same thing. So with quantized inertia, this is quite easy to explain, because the intensity of the vacuum depends on the horizon, the size of the horizon. So if you put microwaves into the cavity, then every time they go to the wide end, they gain inertial mass, because more Unruh waves are allowed there. And every time they move towards the narrow end, these photons lose inertial mass. So if they bounce around, you're going to get a general shift of the microwave energy towards that side, and the cavity will have to move the other way. So you can imagine a man on a ship. Every time he walks to the back of the ship, he picks up a weight and carries it to the back and puts it down. Then he walks to the front again, and he walks to the back again, picks up a weight, takes it to the back. The centre of mass of the ship is moving to the back, so the ship has got to move the other way. So, using quantized inertia, you can predict quite well the thrusts of the M drive. So these are the various experiments that have been done by Scheuer, by NASA, by Martin Timar in Germany. These are the observed thrusts in millinewtons. It's still a very small thrust, but it's measurable. And these are the predicted ones from quantized inertia, so it's not bad. This is the formula I'm using, and if you notice, there are no adjustable parameters in there. It's just the power you put in, the quality factor of the chamber, so that's a measured thing. It's the amount of polish on the inside of the chamber, the goodness of the mirror that they have. L is the length, for example. These are all measurable quantities. Then there's another very strange machine that's been making a controversy in America, the Woodward effect, or Mach effect thrusters. What Woodward tends to do is he has a piezoelectric material here. He puts an AC electromagnetic signal in to make it vibrate. He has a brass end cap on one end and a smaller end cap on the other, and he finds a thrust which is towards a big brass end cap. So Woodward's theory itself does not predict this. I've tried to show that. That's his formula there for the force, and it predicts. I'm not quite sure what he means in his paper actually. There's this strange parameter here, but it's either 192 kilonewtons or 0.05 micronewtons, and the thrust measured in this particular experiment was 5 micronewtons. So Woodward's theory does not predict his experiments, but quantized inertia does. If you assume it's like the M drive, and the large brass cap blocks out Unruh waves, but the thin cap doesn't block out as many, then you'll get more Unruh waves hitting the object from this side than from this side, so it should move that way. And using the same formula I used for the M drive, this is a simpler version of it, I predict this 24 micronewtons, which is not too far from 5. And to do this, I've assumed that the large brass cap gets rid of all the Unruh waves, and the thin brass cap doesn't get rid of any. So that's kind of an extreme assumption. It's probably not going to be as intense as that. So the fact that this is bigger makes sense. So, well, I've just received some funding from DARPA, the Defence Advanced Research Project Agency. So that's about £1 million over 4 years. And they want me to do two things. They want me to make quantized inertia more predictive, so more exact. At the moment I just do it all on paper. They want a computer model. And also demonstrate the capability to counter gravity, to launch or at least thrust things with it, which are things that I've been alluding to. So there are 3 ways I'm going to try and do this. The first is in collaboration with a professor in Spain. We're going to put laser into a fibre optic loop, so it will accelerate fast, see under waves, and then put a shield on one side to see if it will thrust. So for a power input of 2 watts, for example, at these values, there should be a thrust of about 6 micronewtons. And this guy in Spain has a superconducting track, so he can measure very small motions. Second way, a guy called Travis Taylor in America read one of my papers, and he pointed out to me that you could do this using optics instead. You could have 2 mirrors, instead of an M drive, 2 different mirrors of different sizes, and bounce laser light between those mirrors. So Martin Timar in Germany is going to try to build one of these for me. And then the third method is quite interesting. We haven't got an experiment to do this yet, but it could be that if you have a kind of grid like this, and then you spin it, you spin the object, then under waves more will be allowed at the bottom than in the fine mesh at the top, so there should be a force pushing up. And this always reminds me of Kletnov's experiment. If you remember, Paul Kletnov, he had a superconducting disk, and the top surface of it had very small grains of superconducting crystal, and the bottom had a slab with very large grains, and he got a force upwards as well. So, but we haven't set up an experiment to do this yet. Okay, so I've just described quantized inertia. It unifies physics because it combines relativity and quantum mechanics. It gets rid of dark matter, and it proposes there may be something like a horizon drive, which would be very, very useful. I might do something like this. Thanks very much for inviting me.